In this video, we are to discuss on autocorrelation function of time series. What is the autocorrelation function? The autocorrelation function, denoted as this, it measures the linear relationship between variables, often measured from -1 to 1. Now, the ACF measures relationships of variables from -1 to +1. First, before we go on that, we take the properties of ACF. One of the properties of ACF is the ACF is equal to 1. The second property is that the ACF is equal to -k. And the third property of the ACF is that the ACF is less than or equal to the ACF of naught. So these are the three properties of the autocorrelation function. Now, the Walker equation is used to explain the autocorrelation function. The Walker equation. The Walker equation is used to explain the autocorrelation function of a time series. So we have to do this. Now, we say the consider the autoregressive model of order P. Consider autoregressive model of order P process. This process can be written as ft to be equal to phi1 x t minus 1 plus phi2 x t minus 2 plus, it continues like that, phi p x t minus p. So we can write this as our autoregressive model of order P. So this is what we get from the model. This is what we get from the model. How do we use the Walker equation to explain the autocorrelation function? The first thing to do is to multiply by x t minus k. We say multiply through by xt minus k. So if you are multiplying the left hand side and the right hand side by xt minus k, we have something like this. Xt minus k multiplied by xt to be equal to phi 1 xt minus k multiplied by xt plus phi 2 xt minus k multiplied by xt minus 2 plus phi p xt minus k multiplied by xt minus p. Now, why we did not include the error term here is because if you multiply this by this, if you take the expectation, what happens is that it returns to zero. So it's an error term. That is why we excluded it. So if we have this, what is the next thing to do? The next thing to do is to take the expectation. Is to take the expectation. So we take the expectation. Take the expectation. So if you take the expectation, it then means it will have to affect both the left hand side and the right hand side. So taking the expectation, we can write it as this. The expectation of xt minus k xt to be equal to, this is a constant, so we say the expectation of xt minus k xt plus phi 2, the expectation of xt minus k xt minus 2 plus phi p, the expectation of xt minus k, then xt minus p. This is what we get. Now, we should also recall that from autocorrelation function, you should also recall that Rk is equal to the covariance of S P minus K, then Xt. So it then means that wherever we see this, we put our arrow key. Wherever we see this, we put our arrow key. Because this is also equal to the expectation of this and this. So the next thing to do is for we to move over to this side of the board. Move over to this side of the board. For more on this topic, you need to subscribe to this channel. So wherever we see this, we put, it then means that RK is equal to pi 1. The rule of this is RK. RK plus pi 2 RK plus pi p RK. So this is what we have. But we should recall that, say recall that our autocorrelation function is equal to RK all over R naught. So we can say divide both sides by R naught. So we have RK all over R naught is equal to pi 1 RK all over R naught plus pi 2 RK all over R naught plus, it continues to give us pi p RK all over R0. So of course, we know that the whole of this will give us our autocorrelation function. The whole of this will give us our autocorrelation function. So we move over to this side of the board. For more on this topic, you need to subscribe to this channel. So it then means that the whole of this will give us this. So we say since the autocorrelation function is equal to RK all over R0, it then means that wherever we see this, we put our autocorrelation function. So our autocorrelation function will now be equal to pi 1 pk minus 1 plus pi 2 pk minus 2 plus pi p, then p k. So that's what we get. Sorry, pi 1 pk minus 1 plus pi 2 pk minus 2, okay, plus pi p pk minus p. So what do we need to do? We can now write the whole of this we have here in the matrix form. That means writing the Walker equation. The Walker equation can be written as, after writing this, we can say the Walker equation can be written as, now we use the whole of this to form our matrix. We use the whole of that to form our matrix. For this we have P1 autocovariance P and PK. The next on the list we have this again. So we can write one, we come here, we write autocovariance, autocovariance here. We can write P1 and it continues to give us K minus 1. This one here, we can write it as 1 because we have a diagonal here. Also, we have this, and it continues to give us K minus 1, K minus 2, and it continues. This continues here, or you write K minus 2, K minus 3, and 1. Also, we know we have our parameter coefficient. So we can put it here to now multiply this. We have it at pi 1, pi 2, we continue to pi So this is what we get. This is what we get. We can simply write the whole of this. We move over to this side of the board. This is what we get. We want to write our Walker equation. Our Walker equation, which is used to explain the autocovariance, which is used to explain the autocorrelation function, can be written as this. If we have gone through all the processes. Now we can also write it as PA to be equal to PN pi. So this is exactly what we just got. This is exactly what we got from our Walker equation. So this can be expressed in the Walker equation. For more on this topic, we need to subscribe to this channel.